This is the third and last Stata clip about panel data. And in this clip I would like to do two things. First of all, I would like to show you the effect of clustering with standard errors. And the second thing what I would like to discuss is the Hausman test on fixed or random effects. And again, we based our results on the survey, which is the data set we used during the whole lecture about panel data in Stata, right? So I hope you're familiar with the data set right now a bit. We have young women, a panel data set, a survey. And we would like to explain the log of the wage. As always, you should tell Stata first that you use panel data with this XT set, an ID code the I and a year the T. And remember, we have an unbalanced panel data set. So let's first do a very simple pooled regression with the race, call grade, the age, and so on. The known variables is also used in the previous clip, and have a look at the T statistics. So you see most of them, they are all significant, which means that in absolute sense they are bigger than 2, such that you can reject the null hypothesis that the beta is equal to 0, except the MSP. With all the other variables you see there statistically significant. However, the standard errors here may be wrong because they are based on the assumption that the epsilons are uncorrelated either within a particular person over time or at a particular time period across all the individuals. On top of that, there might be the case that the variance of my epsilons is maybe completely different than yours. So what you're going to do first is you're going to repeat the regression, but now I type VCE and then between parentheses cluster, and I cluster now first on individual. So that means that I'm going to look to my own epsilons through time, and then I cluster these epsilons. So I account for the possible correlation over there. So what happens if you do that? Well, you see that some T statistics, they decrease. Put differently, the standard errors become slightly higher. Are we allowed to use, by the way, this clustering method? Yes, because we have a lot of clusters. You see, you need at least 50. Here we have 4,000 something, so that's okay. So, for example, you see here the race, 0.005, now it becomes 0.010, twice as large. Another example is, for example, grade. Here you see 0.0016, and here grade is 0.0032. So it's almost a factor 2. So put differently, indeed, we need to cluster on individual. Now, a next thing which you could also do is cluster on time. So then I type VCE, and then between parentheses cluster now in year. So what happens now, and let's rerun the first regression without any clustering again, just for comparative reasons. So now you see there is some effect, but not that much, right? So here you see minus 12, minus 10, 8 are almost the same, 22 and 12. Here you see even that grade, that is quite a difference, right? So grade still decreases from 39 to 22.9. So put differently, indeed, the standard error now increases 0.027. Well, first of all, it was 0.0015. Another example is the 10-year, very important one, 0.0029. And here it was 0.0009. So the T statistic decreased from 23 to 7. So you see that either if we cluster on time or if we cluster on individual, then the standard errors increases. But the most increase you see here when you cluster on the individual. And by the way, be careful, clustering on time is maybe a bit problematic because we have only 15 of these clusters. And remember, you need at least 50 clusters. So maybe you can take these robust standard errors with respect to time a bit with a grain of salt. Now there is one thing that I did not tell you. Maybe it is a bit, I don't know, maybe you think, this Anne is a bit of a funny man, because you thought already by yourself, why on earth do we use a pooled regression? And that's a very good question. So I showed you the effect of clustering only in the slide with respect to pooled regression. And of course it is for a reason. So what I want to do now is I want to use fixed effects. Okay. Remember from the previous video on Stata with respect to panel data, race, score grade and grade, of course they will drop out because they do not depend on time. And have a look now to the standard errors. And now within this individual fixed effects, I again run this regression, but now I cluster on individual. And what do you see in general? That minus 3.5, minus 2, 19 reduces to 12, 12 reduces to 8. So what I want to say here is that if you already have firm fixed effects or here individual fixed effects, that already take into account some of the correlation that we talked about. So put differently, if you allow for different alpha I per individual, that takes away already some of the possible autocorrelation that's there in the epsilons. And that's why you see now that the standard errors here of fixed effects, here fixed effects robust, yes, they still increase a bit, but it's much less than if we compared here the difference between the original regression and the pooled regression with robust standard errors with clustering through. So here the difference is much more compared to over here. So the takeaway is, if you already have individual fixed effects, yes, you could again use clustered standard errors, but you see that the effect is less than if you compare the standard errors of a pooled regression versus the standard errors with a pooled regression with clustering. Okay, that was part 1 of my video. And now the second part is that I would like to ask the question, should we use individual fixed effects or should we use individual random effects? Well, in order to answer that question, we should do the Hausman test, right? So remember from the class, on the slides, first we do the regression with fixed effects. By the way, don't use clustered standard errors because then Stata is gonna complain. So now I store the results. I call this FE result. And now I also gonna run the random effects model with comma RE. Okay. Of course, now race is allowed. Of course, also grade is allowed because remember, random effect says this individual effect is treated as random. So we put in the error term. So yes, we are allowed to take into account variables that only depend on I. And I also going to store these estimates. And I call them RE result. And now remember, what is the Hausman test doing? Well, it compares the betas under the fixed effects estimation with the betas under the random effects. And remember, if there was a huge correlation between the X and this individual effect, UI, then there was could be a huge bias in the beta of the random effects. So here you see the differences. Well, there are some differences, right? With respect to age, but also maybe with respect to the MSP. However, the variance is also quite big. But still, you see that the chi-square distribution says we have a value of 82, right? And the p-value is equal to 0. So what does it mean? That we reject the null hypothesis that there is no correlation between the X variables and the UI. Put differently, we really should use individual fixed effects. We could have seen this already a bit. Why? Well, because here you see the correlation indeed between the UI and the X variable is equal to 0.16. And remember, with the random effects, you assume that is equal to 0. So this already gave us sort of an indication that, hey, be careful, maybe you are not allowed to use random effects. Now, this test indeed confirms that and says, yes, there's quite some standard deviation here, but still, the difference here, for example, between h is a factor 1.5, right? Minus 0.030, minus 0.046. And also the MSP is quite a large difference, relatively spoken. And also the hours has quite some differences. So we conclude, we reject the null hypothesis, and we are not allowed to use random effects. So instead, we should use individual fixed effects.